Hey everyone! So today we're looking at something really interesting in science. There's this law that's supposed to be perfect, super simple, always works. But in the real world, it kind of breaks all the time. So the big question is, why does a perfect law, not seem so perfect?
Okay, so the law we're talking about is called Beers' law, and it's a huge deal in chemistry labs. The idea is actually super simple. You take a colored liquid, the more concentrated it is, the more light it soaks up. Right? More color means more light gets absorbed. If you double the amount of stuff in there, you should double the light it absorbs. It's supposed to be this perfectly clean, straight-line relationship.
So what that means is, if you were to make a graph of this, plotting how much light gets absorbed against how concentrated the solution is, you should always get a perfect straight line. I mean, it's a law, right? But here's where it gets weird. In real life, scientists run these tests, and they get these weird bent curves. So what's the deal? If the law is the law, what on earth is breaking it?
All right, so this graph right here, this is our crime scene. That curve you see, that's the evidence. It's a clear violation of that straight line we were supposed to get. So for the next few minutes, we're going to be detectives. Let's figure out what's causing this beautiful, elegant law to go rogue.
First up in our investigation, the molecules themselves. Yeah, our number one suspect is the stuff in the solution. It turns out, sometimes the problem isn't with the law at all. It's about how the substance is misbehaving.
And here is our first big clue. The science tells us that Beers' law is what's called a limiting law. That's just a fancy way of saying it was only ever designed to be perfect under very specific conditions. And the big one here is that it really only works for super dilute solutions. We're talking ideally below a concentration of 0.01 molar. That's not very concentrated at all.
Let me give you an analogy. A dilute solution is like a party with only a few people in a giant ballroom. Everyone's got tons of space, they're not bumping into each other, they're just doing their own thing. But a concentrated solution, that's a packed house party. People are shoulder to shoulder, bumping into each other, talking, interacting. Their behavior changes. Well, molecules do the exact same thing. When you cram them together, they start interacting and messing with each other's ability to absorb light. And that is what causes these so-called real deviations from the law.
Okay, so we've got one culprit. The solution is just too crowded. But what happens if a scientist is really careful? They make sure the solution is dilute, and the line still bends. That tells us there have to be other suspects in the lineup.
And that brings us to our second suspect, something called chemical deviations. This is when the stuff you're trying to measure doesn't just, sit there. Nope, it's active. It might start reacting with the liquid it's in, or it might break apart into smaller pieces, or even clump together. The point is, it's changing its identity, creating new things that absorb light in a totally different way. And that just throws a wrench in the whole straight line expectation.
Now let's go back to our original crime scene graph. It turns out this is a textbook example of a chemical deviation. What's happening here is that the chemical, an indicator, is literally breaking apart as the concentration changes. So you end up with a mix of the original molecule and its broken down form. Since both of those absorb light differently, you get this classic curve instead of a nice, clean line. So for this particular graph, case closed.
All right, so far we've been pointing the finger at the chemicals. But what if the substance is behaving perfectly and something else is wrong? Well, sometimes the problem isn't the suspect, it's the equipment. The fault can actually be in the machine doing the measuring. These are what we call instrumental deviations.
Problem number one with the machine is something called polychromatic radiation. See, Beers' law has a really important assumption. It assumes you're using a perfectly pure single color of light. Think one specific shade of green and nothing else. That's monochromatic. But in the real world, a lot of instruments aren't perfect. They might accidentally send a little mix of colors through, polychromatic light. And using a mix of light to get a precise measurement, it's kind of like trying to measure something with a stretched out wonky ruler. Your readings are just going to be off.
And you can see it right here. When the light is pure and narrow, like band A, look at that, a perfect straight line, just like the law says. But if the machine is using a wider, messier band of light, like band B, well, different molecules in the sample absorb those different colors unevenly. And the end result? The relationship isn't a straight line anymore. The graph starts to curve downwards.
Okay, the second major machine flaw is called stray light. The best way to think about this is like light pollution inside the instrument. It's just random light bouncing around from tiny scratches or reflections, and it manages to hit the sensor without ever even going through your sample. It's basically contaminating your reading.
And the effect of this stray light is actually super predictable. What it does is create an artificial ceiling, a limit,
on how high the reading can go. So as you make your sample more and more concentrated, it should be absorbing more and more light. But because you've got this constant extra stray light hitting the detector, the machine thinks less light is being absorbed than there really is. And eventually you hit a point where the reading just stops. It flatlines, creating this very specific downward curve.
So, we've rounded up our main culprits. We've seen how they can mess up our perfect line. But does all of this mean Beers' law is useless or a bad law? Absolutely not. In fact, it's the opposite. In science, understanding why and when a law breaks is just as important as knowing the law in the first place.
So let's do a quick recap of our detective work. We found 4 main reasons that Beers' law seems to go off the rails. 1. The solution is just too concentrated. 2. The chemical itself is changing or reacting. 3. The light source from the machine isn't pure. And 4. You've got stray light sneaking in and messing with the detector.
You know, there's a quote that just sums this all up perfectly. Limiting laws in science are those that hold true under limiting conditions. And that's exactly what Beers' law is. It's not wrong, it's a perfect model for a perfect ideal world. The thing is, the real world isn't always so neat, and that's why we see these curves. The law gives us the perfect straight line to compare reality against.
And at the end of the day, learning about all the ways this can go wrong isn't about blaming the law, it's about what makes for better science. When you know why that line might bend, you can design smarter experiments, you can spot when your data looks a little off, and you can understand your results on a whole different level.
So I want to leave you with this final thought. Beers' law seems so simple on the surface, right? But once you actually try to use it, you uncover this entire world of complexity. And if that's true for a pretty fundamental, straightforward law like this, what does that tell us about our bigger mission to understand really complex things? Maybe it teaches us that science isn't really about finding flawless, perfect rules that never break. Maybe it's about building models and then learning from their imperfections to get a clearer and clearer picture of our beautiful, complicated, and yeah, kind of messy universe. Thanks for digging into this with me.